Emergency system overcurrent devices must be selectively coordinated with all supply-side overcurrent protective devices. This requirement, detailed in the National Electrical Code Section 700.27, is crucial for ensuring the reliability of emergency power systems. Selective coordination means that when a fault occurs in the emergency system, only the overcurrent device closest to the fault should open, isolating the problem while allowing the rest of the system to continue operating. This is essential for maintaining power to critical loads during emergencies, such as lighting, fire pumps, and life safety equipment. Achieving selective coordination involves a detailed analysis of the overcurrent protective devices within the emergency system and those on the supply side, typically the utility or a generator. Firstly, the available fault current at various points in the system needs to be determined. This involves calculating the maximum and minimum fault currents that can occur at each point, taking into account the impedance of the conductors, transformers, and other equipment. Secondly, the time current characteristics of the overcurrent devices must be analyzed. This is typically done using time current curves, which show the amount of time it takes for a device to trip at different levels of overcurrent. The goal is to ensure that the downstream devices trip faster than the upstream devices for any given fault current. Thirdly, consider the types of overcurrent devices used in the system. Fuses, circuit breakers, and other protective devices have different time current characteristics, and the selection of appropriate devices is critical for achieving selective coordination. Fuses, for example, can be faster acting than circuit breakers, but they must be replaced after each operation. Circuit breakers can be reset, but they may have a longer clearing time. Fourthly, a coordination study should be performed by a qualified electrical engineer who has experience in power system protection. The engineer will use specialized software to model the system and analyze the time current curves of the overcurrent devices. The study will identify any coordination problems and recommend solutions such as changing the size or type of overcurrent devices, adjusting the settings of the devices, or adding additional protective devices. Fifthly, it is important to document the coordination study and maintain it for future reference. The documentation should include the system one-line diagram, the fault current calculations, the time current curves, and the recommendations of the engineer. This documentation will be helpful for troubleshooting problems and for making changes to the system in the future. Sixthly, regular testing and maintenance of the overcurrent devices are essential for ensuring that they will operate properly when needed. This includes testing the devices to verify that they trip at the correct current and time, and inspecting the devices for any signs of damage or wear. Seventhly, consider the impact of motor starting currents on the coordination of the overcurrent devices. Motors draw a large amount of current when they start, and this current can cause overcurrent devices to trip unnecessarily. To avoid this, it may be necessary to use overcurrent devices that are specifically designed for motor starting applications, or to use motor starters that limit the starting current. Eighthly, consider the impact of harmonic currents on the coordination of the overcurrent devices. Harmonic currents are caused by nonlinear loads such as electronic equipment, and they can distort the voltage and current waveforms. This distortion can cause overcurrent devices to trip unnecessarily, or it can prevent them from tripping when they should. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to use overcurrent devices that are specifically designed to operate in the presence of harmonic current. Ninthly, it's essential to understand the difference between selective coordination and series ratings. Selective coordination ensures that only the closest upstream device trips during a fault, while series ratings allow downstream devices to be protected by an upstream device with a higher interrupting rating. While series ratings can reduce costs, they don't provide the same level of reliability as selective coordination, because a fault can cause multiple devices to trip, shutting down more of the system. Tenthly, consider the voltage drop across the overcurrent devices. Overcurrent devices can introduce a voltage drop into the system, which can affect the performance of sensitive equipment. The voltage drop should be minimized by selecting overcurrent devices with a low impedance. To elaborate further, when performing a coordination study, Specific software tools are often used to simulate the behavior of the electrical system under various fault conditions. These tools allow engineers to visualize the time current curves of different overcurrent devices and ensure that they are properly coordinated. The process often involves adjusting the settings of adjustable trip circuit breakers. These settings include the long-time pickup, short-time pickup, instantaneous pickup, and ground fault pickup. The long-time pickup setting determines the amount of current that the circuit breaker will carry continuously without tripping. The short-time pickup setting determines the amount of current that the circuit breaker will carry for a short period of time before tripping. The instantaneous pickup setting determines the amount of current that the circuit breaker will trip instantaneously. The ground fault pickup setting determines the amount of current that the circuit breaker will trip on a ground fault. Coordination studies must consider both the magnitude and duration of fault currents. Different types of faults, such as bolted faults and arcing faults, will produce different levels of fault current. Bolted faults are characterized by a direct short circuit resulting in very high fault currents. Arcing faults involve an electrical arc, which limits the fault current to a low level. The coordination study must take into account the potential for both types of faults. The National Electrical Code provides guidance on the selection and coordination of overcurrent devices. Section 240 covers overcurrent protection in general, while Section 700 provides specific requirements for emergency systems. Compliance with these requirements is essential for ensuring the safety and reliability of electrical systems. In addition to selective coordination, the National Electrical Code also requires that emergency systems be designed to minimize the impact of a single point of failure. This means that the system should be designed so that a failure of any one component will not cause the entire system to shut down. This can be achieved by using redundant components and by designing the system so that it can be reconfigured in the event of a failure. Consider the specific application of the emergency system when performing the coordination study. For example, a hospital emergency system will have different requirements than a data center emergency system. Hospitals require a high level of reliability to ensure the safety of patients, while data centers require a high level of availability to ensure that critical data is not lost. Understanding the specific requirements of the application is essential for designing a system that meets those needs. Proper documentation of the coordination study is essential for future maintenance and troubleshooting. The documentation should include a one-line diagram of the electrical system, the time current curves of the overcurrent devices, the fault current calculations, and a summary of the coordination study results. This documentation will be helpful for identifying and resolving coordination problems in the future. Regular testing and maintenance of the emergency system are essential for ensuring that it will operate properly when needed. This includes testing the overcurrent devices to verify that they trip at the correct current and time, and inspecting the system for any signs of damage or wear. Any problems that are identified should be corrected promptly. Selective coordination is not always easy to achieve, especially in complex electrical systems. However, it is essential for ensuring the reliability of emergency systems. By following the guidelines outlined in the National Electrical Code and by working with a qualified electrical engineer, it is possible to design a system that meets the requirements for selective coordination. Remember, the primary goal of selective coordination is to isolate faults and minimize the impact on the rest of the emergency system, ensuring that critical loads remain powered during an emergency. Finally, ongoing training for personnel who maintain and operate the emergency system is crucial. They should be familiar with the system's design, operation, and maintenance procedures. This training will help them to quickly identify and resolve any problems that may arise, ensuring that the system remains reliable.